Good afternoon, friends. I would like to introduce myself. Myself Jaydeep Harjibhai-V.V.P. I am working as an assistant professor in V.V.P Engineering College, Rajkot. So today's topic is application of derivatives. Okay, let us first try to know what is the use of this chapter. This chapter enables us to know the nature of the function in the given interval, whether it is increasing or decreasing, or whether it has a point of inflection or not. Okay, slide please. So these are the topics which we are going to cover. First is monotonic function. Second one is first derivative test for monotonic function. Third is first derivative test for extrema. Next one is concavity. Fifth is second derivative test for concavity. Next is point of inflection, and in the last we will see second derivative test for local extrema. Let us start with the definition of increasing function. What do you mean by increasing function? Suppose f of x be any function which is defined on some interval I, then f of x is said to be increasing function if whenever x1 is less than x2 implies f of x1 is less than f of x2. For any x1 x2 belongs to I, that means value of x is increasing, then value of function must be increasing. Similarly, we can define decreasing function. Suppose f of x is any function, then it is said to be decreasing function whenever x1 is less than x2 implies f of x1 is greater than f of x2. That means value of x is increasing, then value of function must be decreasing. Monotonic function. Now next definition is monotonic function. What do you mean by monotonic function? Any function which is either increasing or decreasing is known as a monotonic function. Okay, let us see one example. We have to show that f of x is equal to x square is increasing function on interval 0 to infinite, and it is decreasing function on minus infinite to 0. Let us first prove that this function table talk please. First we will prove that f of x is equal to x square is increasing function. We will use this symbol for increasing function. On this interval 0 to infinite. Let x1 x2 belongs to 0 to infinite be any two arbitrary points from 0 to infinite with x1 is less than x2. We want to prove value of f of x1 is less than value of f of x2. Table top please. Now we have x1 is less than x2 implies x1 square is less than x2 square. Why this happens? Because x1 and x2 are positive. Okay, but what is our x1 square? X1 square is our f of x1 and x2 square is our f of x2. Okay, so we had start with x1 is less than x2 and we reached at f of x1 is less than f of x2. So this proves that f of x is increasing function on this interval 0 to infinite. This was our interval 0 to infinite. Okay, now we will prove that f of x is equal to x square is decreasing function. We will use this symbol for decreasing function. On minus infinite to 0. By the same process we can prove that let x1 x2 belongs to minus infinite to 0 be any two arbitrary points from this interval minus infinite to 0 with x1 is less than x2. We want to prove that f of x1 is greater than f of x2. Then it will follow that f of x is decreasing function in this interval. Now we have x1 is less than x2, implies x1 square is greater than x2 square. Why this happen? Because x1 and x2 are less than 0. So equality will change. x1 square is greater than x2 square. Implies x1 square it is our f of x1 and x2 square it is our f of x2. So we start with x1 is less than x2 and reached at f of x1 is greater than x2. So it will implies that f of x is decreasing function. So f of x is decreasing function on this interval minus infinite to 0. Okay, side please. Okay, now my question is, suppose we have to find the interval in which f of x is equal to x square is increasing or decreasing. Then it is not always easy to find such an interval. For that we have one provision, namely first derivative test for monotonic function. Before we proceed, let us first define critical point. What do you mean by critical points? Suppose f of x is any function defined on interval I and a belongs to I, then a is said to be critical point of f of x if either f of a is equal to 0 or f dash of a is equal to 0 or f dash of a is undefined. F dash of a is undefined. Let us see one example. Find critical point of this function f of x is equal to x square minus 4x. Okay, we have solution. We have function f of x is equal to x square minus 4x. We want to prove the critical point of the what are the critical point of this function. We have f of x is equal to x square minus 4x. So first of all find f dash of x. F dash of x is equal to differentiation of x square is 2x and differentiation of 4x is 4. If we equate f dash of x is equal to 0, then solution of this equation will be our critical points. F dash of x is equal to 0 implies f dash of x is our 2x minus 4, it is our f dash of x is equal to 0 implies 2x is equal to 4 implies x is equal to 2. So this is the critical point of f of x is equal to x square minus 4x. Okay, side please. Now let us proceed first derivative test for monotonic function. Suppose f of x is any continuous function defined on closed interval ab and continuous on closed interval ab and differentiable on open interval ab. Then if f dash of x is greater than 0 for every x belongs to ab, then f of x is increasing function on open interval ab. And if f dash of x is less than 0 for every x belongs to ab, then f of x is decreasing function on this interval ab. Okay, let us try to prove this theorem first. Tabletop please. Let x1 x2 belongs to closed interval ab with x1 is less than x2. Okay, consider this interval closed interval x2 x1 to x2, then f of x is continuous on this interval x1 to x2 and differentiable on open interval x1 to x2. Why? Because x1 x2 is subset of this interval AB, and it is given that f of x is continuous on this interval and differentiable in open interval AB, and as x1 x2 is a sub interval of this interval, so it will follows that f of x is continuous on closed interval AB, x1 x2 and differentiable on this interval x1 to x2. So by Lagrange mean value theorem, we have there exists at least one point C belongs to open interval x1 to x2 such that f dash of C is equal to f of x2 minus f of x1 upon x2 minus x1. It will implies that f of x2 minus f of x1 is equal to f dash of C into x2 minus x1. Give this equation number 1. Okay. Now we consider that if f dash of x is greater than 0, for every x belongs to this interval AB, okay, then in particular we have f dash of C is greater than 0, because reason is that C from this interval A to B. Okay, this is the reason why f dash of C is greater than 0, because f dash of x is greater than 0 for every x belongs to AB and C belongs to this interval, so it will follows that f dash of C is greater than 0. Now see equation number 1. Side please. Sorry. So f dash of C is greater than 0 implies f dash of C into x2 minus x1 is greater than 0. Why? Because x2 is greater than x1 implies x2 minus x1 is greater than 0. Okay. But what is this? From equation number 1 we have f dash of C into x2 minus x1. It is our f of x2 minus f of x1. It is greater than 0. Okay. Implies f of x2 is greater than f of x1. Okay, so we had start with x1 is less than x2 and reach at f of x2 is greater than f of x1, when under which condition, if f dash of x is greater than 0, then we have f of x2 is greater than f of x1. So if f dash of x is greater than 0 for every x belongs to open interval AB, then f of x is increasing function on this interval AB. Okay. Now consider second case. Suppose if f dash of x is less than 0 for every x belongs to this interval AB, then f dash of C is less than 0 in particular, because C is from this interval. Okay, implies f dash of C into x2 minus x1 is less than 0. By the same reason, x2 minus x1 is less than 0, greater than 0. So this is less than 0, this is greater than 0, so again it is less than 0. But this is by the same reason, this is our f of x2 minus f of x1 is less than 0, which implies that f of x2 is less than f of x1. Okay, so if f dash of x is less than 0 for every x belongs to AB, then whenever x1 is less than x2, we have f of x1 is greater than f of x2, so f of x is decreasing function. Okay, we had two cases. If f dash of x is greater than 0, then we prove that f of x is increasing function, and in this case we had proved that if f dash of x is less than 0, then f of x is decreasing function on interval AB. Okay, this completes the proof. Okay, side please. Okay, these are the steps how we can apply first derivative test. Suppose f of x is any function defined on closed interval AB, then first of all we have to find the critical point of f of x. By solving f dash of x is equal to 0, we can have critical points of any function f of x. Second step is, suppose c1 and c2 are the critical points of f of x, then form the intervals, three intervals, a to c1, c1 to c2 and c2 to b. Third one is, then find sign of f dash of x in all the intervals. How can you find the sign of f dash of x? By just evaluating the sign of f dash of x only at one point from that interval, because f dash of x does not change sign from that interval. Okay, because f dash of c1 is equal to 0 and f dash of c2 is equal to 0. Okay, so for using first derivative test, we have to apply all these three steps. Okay, let us see one more example. Using first derivative test for monotonic function, find the critical points of the following function and identify the intervals in which f of x is increasing and decreasing. We have f of x is equal to x cube minus x. Okay, we have to find critical point of this function, and also we have to find the intervals in which f of x is increasing and decreasing function. Okay, let us try to solve this example. Here our f of x is equal to x cube minus 3. First of all, we have to find the critical point of this function. For that we need f dash of x. F dash of x is equal to 3x square minus 1. If we equate f dash of x is equal to 0, then we have 3x square minus 1 is equal to 0, which implies that x square is equal to 1 by 3, implies x is equal to